Alright, so in previous videos we've talked about the idea of a partial derivative, and I've kind of introduced that idea to look something like this. So you have, for example, function f, and you're trying to find its partial derivative with respect to x. And, it can have, for example, two variables, x and y. And so we define the partial derivative, at least in limit terminology, as just being the limit as h goes to 0, where we're trying to find the limit of f of x plus h, x plus h comma y minus the original function f of x, y. All of that over h because we're trying to find the rate of change. Alright, so we've defined the partial derivative as such, but there's no reason that we don't, or we can't, add another variable in this definition. So we could very much, for example, add a z, which would be a third variable in this whole definition of what a partial derivative is. So we could hypothetically have, for example, the partial derivative of f with respect to x with a function that has inputs x, y, and z. And so that what that looks like, again, in limit terminology, it's the same thing except you're adding another variable, and that other variable would be z. So it's f of x plus h, y, comma z, minus, again, the original function, f of x, y, and z. All of that, again, over h because we're trying to find a rate of change. All right, so that is the definition of, at least for three variables, the definition of a partial derivative using limits. And in fact, you can actually do this in general if u is a function, or f, for example, if f is a function of however many variables, its partial derivatives with respect to a certain variable can be defined using the following notation. And so I'm going to break this down for you. However, we know that this is our partial derivative notation, and we're going to call this x sub I over here as, a number of variables. X sub I could be, the first variable, it could be the fifth variable, or the 100th variable. It really doesn't matter, but we're going to use the I here to denote the variable number. And then our limit notation is simply going to indicate the same thing, the limit as h goes to 0. And then we could have any number of variables inside of our function. So we start off from x to 1, x sub 1, dot, 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 and then we could go to x sub I minus 1, and then we go to x sub I, and then we put our plus h in there, and then we can continue on to dot, 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 and then that can be for any n number of variables. And so let me actually scroll so that you can actually see this whole function. And so it's going to look something like this, and then we can close our parentheses, and then we're essentially going to be subtracting just the original function. And that original function is going to start, once again, from the first variable, our ith variable, all the way to our nth variable. Let me somehow scroll a little bit more so you can actually see this. And so it goes all the way to our nth variable, and then all of that over h, because once again, this is rate of change. We're essentially trying to find the change in f with respect to any given variable in our function. So we can do this for a number of different variables. And so that is kind of what we're going to be discussing today, which is partial derivatives with many functions. And the problems for these might seem very challenging at first, but realistically all we have to do is just treat each variable as a constant, and then we can find its partial derivatives. And we'll also be talking about implicit differentiation as well. But first we'll look over a quick sample problem for partial differentiation with 3 or more variables. Alright, this question is asking us to find the first partial derivatives of the following function. The following function being f of x, y, z is equal to y tan x plus 2z. Alright, so the first partial derivatives, that would essentially be the change in f with respect to both with respect to x, y, and z. Alright, so let's first, let's do it with the easy one. I think the easiest one for this is going to be the partial derivative with respect to y. The reason being is just y is an isolated variable over here. And so the partial derivative is simply going to be treating everything else as a constant. So this whole tan x plus 2z is just a constant. And so for a normal derivative, all we would have to do is just take out that tan x plus 2z, and we'll just leave the y normal as 1. And so we're left essentially with just tan x plus 2z. So that's the partial derivative of f with respect to y. All right, so now we have to find the partial derivative of, let's go with x, because that is the second easiest, I would say. Okay, so partial derivative of f with respect to x. How are we going to do this? Well, y is going to be a constant. We know that the derivative of tan of anything is going to be secant squared. And so we write that down. So y is equal to secant squared x plus 2z. However, we also need to now institute chain rule. And so with chain rule, what we have to do is that treating z as a constant, because we're not trying to find its partial derivative, but treating z as a constant, we know that the partial derivative of the derivative of x plus 2z is simply going to be 1. So we're left with the the expression as is. And so this is going to be our partial derivative of f with respect to x. Finally, for z, for z, the partial derivative of f with respect to z, what we have here is, again, we're treating y as a constant. The derivative of tan is going to be secant squared. So we're left with y secant squared x plus 2z, much like the previous one, except this time now we have to derive x plus 2z using chain rule, and it's going to be a little different this time because now we're treating x as the constant. And so the derivative of x plus 2z treating x as a constant is just going to be 2, because we have that 2 lingering in front of the z. And so we have 2 right over there. Just simplifying it a bit further, just notation-wise, we are left with 2y secant squared x plus 2z. And so those are the partial derivatives of this function. So we have the partial derivative of f with respect to y, with respect to x, and with respect to z. Let's look at another one of these problems. All right, we're asked to find the partial derivatives of the following function, where the function is f of x, y, z equals the square root of x to the fourth plus y squared cosine z. It might look like a complicated function, but if we break this down, we can surely solve it. Okay, so first things first, what we have to do is find the easiest variable to find the partial derivative for. So I'm thinking right now x, because it's kind of in a corner over there. And so what we first have to do is declare that we're trying to find the partial derivative of f with respect to x. Okay, so first, the derivative of this whole thing. If we rewrite this, we can say that x to the fourth plus y squared cosine z to the power of 1 over 2. And so using power rule, we bring down that 1 over 2, and we change the power to negative 1 over 2. And so what this becomes is 1 over 2 root x to the fourth plus y squared cosine z. Okay, let me extend that out a bit. Okay. However, we also need to do chain rule. And so let me actually clear this numerator because it's 1 anyway. So I'm going to clear the numerator, and we're going to put whatever terms come out of this come out of the function for chain rule. We're going to put it up on the numerator. So now, treating y and z as a constant, the derivative of x to the fourth plus y squared cosine z, again, treating y and z as a constant, is just going to be 4x cubed. Because, again, using power rule on the x, we bring down the 4, we change the power to 3, and so we're left with 4x cubed. Everything else is a constant, so that's just 0. And so our partial derivative with respect to x becomes 4x cubed over 2 square root x to the fourth plus y squared cosine z. If we want to simplify this even further, we could just say, we could take out these, the 2 over here, and this just become 2x cubed over x to the fourth plus y squared cosine z. All right, so that is our first partial derivative. The second partial derivative is going to be, let's say, the partial derivative of f with respect to y. All right, so again, we do the same thing as we did for the first one. We again use power rule, and so it's going to end up being 1 over 2 square root x to the fourth plus y squared cosine z. All right, now this time we're treating both x and z as a constant. And so in that regard, the because since we're doing chain rule right now, the x to the fourth becomes 0. The derivative of y squared, meanwhile, is just 2y, because again, using power rule, we bring down the 2, and the power becomes 1, so it's 2y, and then cosine z is just a constant, so we leave it as cosine z. So it becomes, in the numerator at least, it becomes cosine z 2y, or in better terms, 2y cosine z. Canceling out these two 2's, we're left with y cosine z over the square root of x to the fourth plus y squared cosine z. All right, we're on a roll. We can do now the last and final derivative, which is f with respect to z, with confidence. Again, following in the pattern of the previous derivatives, partial derivatives, we know that we have to bring down the power of 1 over 2 and change it to negative 1 over 2. That leaves us with 1 over 2 root x to the fourth plus y squared cosine z. All right, now we're treating x and y as constants. Again, the x becomes 0, much like the partial derivative with respect to y. The y squared is also left as constant, the x to the fourth becomes 0. The y squared is also left as constant. And the derivative of cosine z, well, if we remember our trigonometric derivatives, that's essentially just negative sine z. And so this numerator, at least, becomes negative y squared sine z. And we can leave that as is, nothing cancels out. And so that is our partial derivative of f with respect to z. Let's look at another problem, this time dealing with implicit differentiation. All right, this question is asking us to use implicit differentiation to find the partial derivative of z with respect to x and z with respect to y for the following equation, the equation being e to the power of z is equal to x, y, z, assuming that z, of course, is defined implicitly as a function of x and y. All right, so we first have to break down this problem. In order to find the partial derivatives using implicit differentiation, we need to let's first start off with finding the partial derivative with respect to x. So let me use a different color here. Give 2 seconds. Changing color to, let's say, blue. Yeah, blue is fine. So we have dz over dx. Now, really, the best way to imagine this and the best way to kind of think about this is kind of we're finding the partial derivatives kind of piece by piece and term by term. Okay? I'm going to explain what that means in a little bit. But first of all, let's try finding the partial derivative of z with respect to x for the term e to the power of z. Well, that is a z-containing term. And so while it's not constant, it is also not x. And so we're definitely going to be left with the partial derivative of z with respect to x. And so what that's going to look like, essentially, is that the derivative of e to the power of z is just e to the power of z. And also, because we're using chain rule, we are left with the derivative, we're left with the partial derivative of z with respect to x. That is going to be equal to, and now what we have here is y, which is going to be a constant, multiplied by x, which is multiplied by z. And so clearly we have to use product rule over here. And the reason we have to use product rule is because we have x and we have z, both of which are non-constant terms in this equation. All right, so let's start off with x because it looks like the easiest one in this situation. And so, actually, let me rewrite this in order to make it more easier for us to understand. And so, I'll write it over here. So, yx and z. All right, so now let's use product rule. All right, so in order to use product rule, we'll first do x, like I said, and so the derivative of just yx, treating y as a constant, is just y. And so what this becomes is just yz. Now we're adding that to yx plus the derivative, yx multiplied by the derivative of z. And the derivative of z is just 1. However, because we have to use chain rule, and also because z is a non-constant term, we're multiplying this by the partial derivative of z with respect to x. And so what we're left with is yx multiplied by del z over del x. Okay, so now we have to solve for the partial derivative of z with respect to x. And so right now we have one term that doesn't contain that, and we have two terms that do. So I'll bring them onto one side. And so what ends up happening is that we have e to the power of z multiplied by del z over del x minus yx del z over del x being equivalent to yz. Let me rewrite that z. Okay. All right. Using the idea of distribution or reverse distribution, if you think about it, we can take out this del z over del x, and it'll then become del z over del x multiplied by e to the power of z minus yx, which is going to all be equivalent to yz. And so hence, using the idea of dividing by both sides, we can hence say that the partial derivative of z with respect to x is going to be yz over e to the power of z minus yx. Okay, let me box that. All right, pretty straightforward starting off. Now let's do the same, but for the partial derivative with respect to y. So let me just scroll down over here. And so let's remind ourselves of what the actual function is, or sorry, the actual equation is. So it's e to the power of z being equal to both yx times z. But now I'm going to rewrite that to instead be xy parentheses z. And I'll explain to you a little later. That just kind of helps me out when trying to find work out when we're doing product rule. All right, so what we have here, let me pull out a different color here. What we have here is we're trying to find del z over del y now. Okay, let me change the color. All right, so first things first. Once again, we're trying to find the partial derivative of, or sorry, the derivative of e to the power of z. Z again is not a constant term in this when we're trying to find this partial derivative. It's not a constant term. It's also not a y-containing term, and so what that means is we'll find its normal derivative. However, we also need to use quote-unquote chain rule, and so in that sense, we have to multiply this by the partial derivative of z with respect to y. All right, then that leaves us with the xy multiplied by z. And so if we remember what we did previously, we can use the same concept. And so first we find the partial derivative, or sorry, the derivative of xy, where x is just a constant. And in that case, it's just x, because y basically, we can remove the y, so it's just, we're just left with x as the derivative. So we have xz added to, because this is product rule, added to the derivative of z. Now the derivative of z, yet again, it's just going to be 1. However, again, it's a non-constant term, so we're multiplying that by the partial derivative of z with respect to y, and so we're left with xy multiplied by the partial derivative of z with respect to y. All right, again, just like previously, we're solving for del z over del y. And so I'm going to fast forward a bit over here, but using the same principle as last time, we can just rewrite this equation as being del z over del y multiplied by ez minus xy being equal to xz. And so simplifying this even further, what that leaves us with is del z over del y being equal to xz over e to the power of z minus xy. And so that becomes our answer. And so that is how we kind of use implicit differentiation in the context of trying to find partial derivatives, assuming that we have a certain variable being defined implicitly. let's look at a final example of implicit differentiation. Right, now we're asked to use implicit differentiation to find del z over del x and del z over del y for the following equation. yz plus x ln y is equal to z squared. Again, we're assuming that z is defined implicitly in this function. Alright, so again, we'll start off by trying to find del z over del x. Let me again use a different color, so del z, whoops, that was a terrible z, del z over del x. Alright, so again, y is going to be a constant throughout, and so we'll start off over here. And so what we have is yz, and so again, z is a non-constant term. However, at the same time, it is not x, and so we have to multiply this by del z over del x. Meanwhile, we have the y lingering over here as a constant, so the derivative of yz is just going to be y. And then we're multiplying this because, yes, we're multiplying this by del z over del x because of the presence of the z. Then we have x ln y. The derivative of x ln y treating y as a constant, if you will remember, is just going to be ln y. We remove the x entirely. And then finally, derivative of z squared is going to be 2z. However, we also have to multiply that by del z over del x because of the presence of a non-constant term that is not x. Yeah, so we'll do 2z multiplied by del z over del x. Okay, so we have our equation here, and now we just have to solve for del z over del x. And so we bring all the del z over del x terms onto one side, we'll bring the ln y onto the other side, and so what we're left with is the following. Y multiplied by del z over del x minus 2z del z over del x is equal to negative ln y. I don't really like the fact that the ln y is negative, and so we might change that later. Alright, so using anti-distribution, we can say that del z over del x can be multiplied by y minus 2z, and it's the same equivalent expression. That is going to be equivalent to negative ln y. Let me scroll down a bit. Okay, so now we can divide both sides by y minus 2z, and we're left with del z over del x being equal to negative ln y over y minus 2z. Since I want to remove the negative, I can transfer it over to the denominator, and we are definitively left with the partial derivative of z with respect to x being 2z minus y. And that is our answer. Alright, we have to do the same thing now for del z, del y. Oops, del z, del y. Alright, let's remind ourselves of the function yet again. So we have yz plus x ln y equals z squared. So again, this time we might have to do product rule over here, and then over here we can just simply take out the x, and then we might have to do chain rule over here. Okay, let me actually, just for the sake of simplicity, let me copy over this function, and let's bring it down over here, just to remind ourselves. Okay, so first things first, we're going to have to use product rule over here because we have two non-constant terms over here, and particularly those two non-constant terms are y and z. And so what we have to do is first let's first derive y, let's first derive y. And so the derivative of y is just going to be 1, because if we use power rule, we're bringing down the 1, changing the power to 0, and so that just amounts to 1, and so we're left with just z. Now the derivative of z is just going to be 1 yet again. However, we're multiplying that by del z over del y. So del z over del y. Okay. Next things is going to be, the next term is going to be x ln y. Now again, we're treating x as a constant over here, so we can completely ignore that. The derivative of ln y is just 1 over y, and so what we're left with is x times 1 over y, which is just x over y. All of that is going to be equal to z squared, or sorry, the derivative of z squared, which is 2z. multiply it again by del z over del y. And when trying to find the derivative of a z-containing term, if you want to just basic understanding, just remember to multiply it by del z over whatever, or just multiply it by whatever partial derivative you're trying to find. Okay, back to the question. We can solve for del z over del y. Again, we're moving all the del z over del y terms onto one side, and otherwise we're moving all the other terms to the other side. In this case, let me keep all the non-del z over del y terms on the left side. And so we have z plus x over y on one side, and we have, and I'm going to quickly simplify over here, we have del z over del y multiplied by 2z minus y on the other side. Okay, simplifying this out, we have del z over del y being equivalent to z plus xy over 2z minus y. However, I'm not a huge fan, again, of the fact that there's a fraction in the numerator itself. So we can simplify this, and this can become zy over y plus x over y over 2z minus y. And then, again, simplifying this out again, and this is not necessarily mandatory, however, you can do it if you so choose. And so what that leaves us with is just going to be x plus yz over y multiplied by 2z minus y. And thus we have not only found the partial derivative of z with respect to y, but we've definitively answered the question. I'll be posting the PDF of this whiteboard onto the description of this YouTube video. Thank you so much for watching. If you have any questions or comments, please leave that in the comment section, and I'll be happy to respond to them. Otherwise, thank you for giving the time to watch this video.